So as we saw in those examples, and we talked about, we cannot validate our conclusions with inductive reasoning, right? If we use inductive reasoning, then there's no sure way to confirm our conclusions. However, we can confirm that a conclusion is not valid or not true by using a counterexample. All right, and so we can use counterexamples to confirm that a conclusion is not true. So if we make a conjecture that says the difference of two integers is less than either integer, there's an infinite amount of possibilities, right, where that is true. So the difference of two integers is less than either integer, right? Like 3 minus 2 is 1. So 1 is less than 3 and it's less than 2, right? And I could continue with the pattern of numbers that are consecutive, right? Like 4 and 5, or 7 and 6, 8 and 9, et cetera, right? And their difference will be 1, and that will of course be less than the two integers that I'm subtracting, right? However, if we just get one counterexample, then we prove that conjecture is not valid, right? So for example, if I find, let's say 7 minus 1, right, that's 6. So 6 is not less than, it's less than 7, but it's not less than 1, right? So it's not less than either integer, right? So that proves the whole conjecture false. Okay. All right. So let's take a look at this next example. It says if the name of the month starts with the letter J, then it is a summer month. And that's true with June and July, right? But not true with January. So January is a counterexample. So that proves this whole conjecture false. This whole statement is false, right? If the name of the month starts with the letter J, then it's a summer month. That's false, okay? That's a false claim. All right. So here are examples. So it says find one counterexample to show that each conjecture is false, right? And sometimes there only is one counterexample to if I say every whole number is positive, right? And if you remember whole numbers, 0, 1, 2, 3, all the way up to infinity, right? No fractions, no decimals, no in-betweenies, just all the I guess numbers that can be expressed as a fraction over 1 maybe is one way you can say that. And anyway, but for whole numbers, 0 is not positive, right? 0 is a whole number and it's not positive. So there's the counterexample. All other whole numbers are positive, right? So I only have one counterexample in that case. But anyway, 1 is all you need to prove a conjecture false. All right. So here we're trying to find one counterexample to show that each conjecture is false. So number 1, the sum of any two odd integers is odd. The sum of any two odd integers is odd. So this one, in fact, I can't find one where that confirms this, or at least supports this conjecture, right? So anytime I add two odd integers, 1 plus 1, that's 2. That's even. 1 plus 3, the weird one. 1 plus 3 is 4, right? And so forth and so on. I can even add negatives. -3 plus -5 is -8, right? That's even, and so forth. So there's a lot of them you can use on this one. So just pick one. All right, number 2, the product of two positive numbers is greater than either number. The product of two positive numbers is greater than either number. So let's see. Two positive numbers. What if... So this seems true, right? If we have like 1 times 2, 2 times 3, we seem to get numbers that are, well, 1 times 2 is 2, so that's not greater than either number. 2 times 3 is 6. That works, right? 3 times 4. So it seems to work with numbers larger than 1, right? But if you use 1, then you get ones that are not greater than, they're equal to, right? Also, if you get into the fraction realm, 1/2 times 1/3, that would be 1/6, which is less than both numbers, right? So, all right, there's a couple counterexamples there. Number 3, a 4-sided figure with 4 right angles is a square. Okay, so a 4-sided figure with 4 right angles is a square. So can I draw a 4-sided figure with 4 right angles that's not a square? Sure can, right? That would be a rectangle. All right, so there's a counterexample. This is an example where I think there's only one counterexample. Number 4, the result of a number multiplied by a positive integer is always larger than the original number. So the result of a number multiplied by a positive number is always larger than the original number. All right, and that's one that's true a lot of the time, right? Like if I have a number, let's say 5, and I multiply by a positive integer like 2, then it becomes bigger, right? I get 10, or 5 times 3, or 7 times 4. So that generally is true, but and a good place to look for counterexamples with ones and zeros, and maybe even fractions or negatives. Try different numbers out. But here it's a positive integer, so we can't try 0 because it's positive. We can't try fractions because it's an integer, right? But if you try 1 gives you an example. Like if I multiply 5 by 1, I get 5, and 5 is not larger than the original number 5, right? It's equal to. So there's our counterexample. All right. So kind of a different type of math. We're in this unit, this chapter, we're dealing with reasoning and proofs, and so we're going to be thinking about how can we validate something, or how can we make conclusions and justify those conclusions. And so that's what we're going to be dealing with. So with inductive reasoning, you cannot validate that your conclusion is true. So you're making a conjecture or kind of an educated guess as to what the situation is based on observations or past experiences or things like that. Okay, so not the best kind of reason, not ideal. Sometimes it's all we have to go on, right? Like the weatherman or woman, right? The weather person is going to be looking at patterns, weather patterns, and looking at the systems heading in and what happened in other places as they come towards our location, right? And so they'll make a conjecture, right? And is the weather person always correct? And the answer is no, right? Sometimes they are, sometimes they aren't. And so and that's the nature of their job, is they're using inductive reasoning to make their conjectures. And so by nature they're going to have some margin of error, right? So all right, so it's not the best reasoning, or if you can use deductive reasoning, which we'll learn about later, that's the way to go. But sometimes that's not an option. Sometimes you have to use inductive reasoning, or that's the best way to make a conclusion. Okay.